exciting career in astronomy that was inspired by his astronomy father. He's a research physicist and senior fellow at the Space Sciences Laboratory at UC Berkeley. He received his PhD at Berkeley in 1992 in high-energy astrophysics, but migrated to planetary sciences. He's been intensively involved in the analyses of the Cometary and interstellar dust collections returned from the Stardust Mission. Most recently, he was the leader of the interstellar preliminary examination for the Stardust Mission, and he's involved in planning for new missions. This includes a new interstellar dust mission and a mission to collect a surface sample from a comet. Tonight's discussion, analysis of cometary and interstellar dust in the lab. Stardust was the first spacecraft ever to bring back to Earth extraterrestrial materials from beyond the moon. It was designed for 2 missions in one spacecraft. Stardust returned the first samples from a known primitive solar body from comet Wild number 2. The Stardust mission also carried a separate collector that was exposed to the interstellar dust stream for 200 days. These tiny rocks are identified by the return collector of a small army of people, more than 30,000 citizen scientists, through a project called Stardust at Home. Of additional interest, microchips with the names of well over 1 million people were inscribed and placed both inside the sample return capsule and on the spacecraft body, which continues its journey. Dr. Westphal will discuss the mission and present results of the laboratory analyses of the samples from these collectors. Please welcome Dr. Andrew Westphal.
Thank you, Linda. Thank you. All right. I like to move around, and so that's why I'm taking the mic, but I'm not used to having the mic in my hand. So if I fade out, please wave at the back so that you can hear me. And can you hear me now?
Yes.
Yes. Okay, great. Okay, so I've been instructed that I need to plug in this and turn on my recording. So I'll do that. Let's see if this works. I need 14 hands. Okay, I'll start talking as I stay here. Okay. I have a colleague at Berkeley named Tim White. Tim is a paleoanthropologist. So Tim leads a research team that goes to Ethiopia once a year to look for ancient fossil hominids. And the way he and his team do this is actually really very clever. So rather than digging a hole in the ground to try to find these fossils, instead what they do is they wait until after the rainy season each year. And it turns out that the rains wash away about 1/4 inch of topsoil. And that uncovers and reveals fossils. And so the way they can find these fossils is by, after the rainy season is over, it's very hot. So they walk across the landscape, hunched over like this, and it's 120 degrees, and there's sweat dripping in their eyes, and it's absolutely, unbelievably miserable. So why do they do this? They do this because they're passionate about trying to understand our origins. They're trying to understand human origins by looking at the clues that are locked in the fossils of our ancestors. Let me show you a picture. So this is one of Tim's colleagues, one of his Ethiopian colleagues, pointing out one of the fossils that was found this way. And it turns out that most fossils, the most durable fossils in the human body, are molars. And so this is a pair of molars from a creature named Afarensis. This is the Afar region. And so this is, this may be a little hard to see in the back, I guess. But see, I have a laser pointer here. But I think you can see it. So there's a pair of molars there. And so they're forced to try to understand and reconstruct as much as they can about this creature based on just the molars that are left. And that's not because that's what they prefer. It's because that's all they've got. So that's what they're forced to do. And And it turns out that these fossils are about 4.5 million years old. So we're engaged in something, we're motivated by much the same thing in our research group. We're trying to understand human origins, not just our origins but our origins in the solar system and the origin of the solar system. And so we go back about 1,000 times further back in time. So this fossil is about 4.5 million years old. We go back to 4.5 billion years. And so this is a cartoon of our solar system about 4.568 billion years ago. This is the time when the solar system was condensing or forming out of interstellar gas and tiny rocks. I'm going to try to avoid the use of the word dust, because dust has such a negative connotation, even though as astronomers you know what I mean. But really these are tiny rocks. And this is the time when the sun and the planets and the comets and the asteroids and all the things that eventually led to us were forming. And so we're trying to understand now this earliest history, the first couple of million years of the solar system's history, based on the clues that are locked in the tiny fossils that we have left over from that time. So lest you think that this is a fanciful cartoon, here's a picture, it's a Hubble picture of HH30. So this is a protostellar system. We're looking at it edge on, and you can see the dust in the plane of the disk, and then these bipolar jets that are often found in these protoplanetary systems. So where do we get these primitive materials? So this is a cartoon of the solar system, hands here. So the sun here on the left, and the march of the planets all the way out to the Kuiper Belt, and then here is the local interstellar medium, just outside the solar system. The first extraterrestrial materials, of course, that we recognized as being extraterrestrial were the meteorites. Starting about 200 years ago, we recognized that these were in fact rocks from space, which seemed like a really nutty idea at the time, but it turned out to be true. And so most of the meteorites come from the asteroids. A handful of meteorites, the so-called SNC meteorites, come from Mars. I need to remember to rotate my microphone at the same time that I turn my head, sorry. And then there are a handful of meteorites that come from the moon, the lunar meteorites. And we recognize them only because we actually have lunar samples from Apollo. The very first samples that we got back that were deliberately brought back, and they weren't delivered to us by nature, but they were delivered to us by spacecraft, were the Apollo samples. From 1969 to 1972, and the Apollo astronauts brought back something like 380 kilograms of materials from the moon. It turns out, and this is kind of a dirty little secret, that less than 5% of that material has been analyzed, but for a very, very good reason, and I'll explain why in a minute. The next extraterrestrial materials that were collected kind of quasi on purpose. They're delivered by nature but had to be collected by high-flying spacecraft in the stratosphere, were these so-called IDPs. IDP, it stands for Interplanetary Dust Particle. It sounds very generic, but it's very specific. It's a very specific kind of object which is found only in the upper atmosphere. And we think there are objects that come both from asteroids and from comets. And so some of them are so-called hydrous IDPs. Come from asteroids, and then some of them so-called CP IDPs, and I'll come back to those, we think come from comets. But maybe not. So it's an interesting mystery that we've uncovered as a part of our research. So the modern era of sample return missions started with the Genesis mission. This is a NASA mission to put a spacecraft between us and the sun and to collect solar wind. So it's really collecting a pure, very clean sample of the sun. Turned out that it wasn't quite as easy as we thought, because the parachute for the spacecraft did not open when it brought the samples back. And so it hit the ground in Utah at about 200 miles an hour, and so the samples were not quite as easy to analyze as everybody anticipated, but it's still delivering fabulous science even now. The mission that I'm going to spend most of my time talking about is the Stardust mission. So as Linda said, this is 2 missions in 1 spacecraft, and it brought back samples in 2006. It brought back samples from a comet called Vil-2, a Jupiter-family comet, and it also brought back, we think, the very first samples from the local interstellar medium, the first solid samples, I should say. So, way out here. So we're filling up this space now with samples from all over the sources. The Japanese space agency, JAXA, launched a mission called Hayabusa, which went to an asteroid and collected a few hundred micrograms of material from the surface of an asteroid called Itokawa. These samples came back in 2010, and a new mission, which I unfortunately didn't manage to put on this slide, is Hayabusa 2, which is another mission from the Japanese Space Agency, which is going to be bringing back much more than that. And just last month, I guess it was about a month ago, NASA's OSIRIS-REx mission launched, and it'll bring back samples from a carbonaceous asteroid in 2023. And then finally, we hope that, and this is a mission that I'm involved with, is to, in the early 2030s, to bring back the very first samples from the surface of a comet. I'll talk more about that. But in parallel with having all of these wonderful samples, one of the things that's incredibly important is the ability to analyze these samples in the laboratory. And it's a bewildering suite of analytical instruments that we now have available to us to analyze all of these samples. They use electron beams, X-ray beams, photon beams, they use ion probes, ion beams. So it all sounds very exotic, and some of these instruments are really cool, really have to say, amazing. And for the people in the field, a really important thing also is being able to take these samples from the state in which we collect them and be able to get them into the state in which we can analyze them. And often that's really hard, and that's often the bottleneck, in fact, in what we do. And those are often very challenging problems. And I'll talk about one of those in just a little bit. So here's another way of looking at progress in laboratory instruments. So many of you may have heard of Moore's Law, which describes the increase in power, computing power, as a function of time, starting way back in the 60s, and that the power of computers doubles, I can't remember what it is, every 18 months or something like that. Probably one of you knows the number better than I do. But the point is that it doubles on a very regular cycle. And something like that has happened with these laboratory instruments. So this is plotting, as a function of time, this is plotting spatial resolution. That is, what are the structures, what are the smallest things you can see with these instruments? And even starting back in the 1870s when people, there was a group, a very famous oceanographic mission called the Challenger mission, which went out to collect, to study the ocean floor, and they discovered these things that they concluded were in fact cosmic spherules. And it was ignored for decades until somebody went back into the records and found, oh, wow, we found these things that long ago. But they could only see roughly sort of what these things were. It wasn't until the 1960s when NASA particularly started investing huge amounts of money, for us anyway, in developing these instruments, largely because of Apollo, that now we can resolve structures that are, instead of 10 microns in size way back in the 1870s, 19th century, now we can resolve things at the 1 angstrom scale. And so this is the dirty secret from Apollo. The reason that only 5% of the Apollo samples have been analyzed is because of this investment. It means that you can analyze with a microgram of material what it used to take a gram to analyze. And so it means you don't need very much. And so that's why the Apollo samples were being largely untouched. So I'm going to talk about early solar system archaeology, and in particular 4 sample return missions, but focusing really on the Stardust mission. And I'll come back to this building here, but this is a building you can see. If it were daylight, you could actually see it through that window across the bay. That's the advanced light source. So, just like Tim White, we might ask these kinds of questions when we're thinking about understanding the early solar system. What are the biases in the fossil record? We've got these fossils. What kind of biases are there? You know, mean, with him, he's very unlikely to find the most fragile bones. They're gone. So you see molars, and then you have to reconstruct things based on just molars. And the same kinds of things happen with us. How complete is this record? What fraction of the most primitive construction materials survive, and how can we even recognize those primitive construction materials? What was the large-scale elemental, chemical, and isotopic structure of the solar nebula? So I showed you that cartoon earlier, but that really is just a cartoon. We'd really like to understand a lot more about what was the structure of that object that ultimately made up us. How did this material move and evolve in the nebula? And then finally, how, when, and where did the macroscopic components of the solar system form? Not just the planets and the asteroids and the comets, but all the other things that are larger than the primitive building blocks that things were constructed from. So I'm going to start in the middle. Talk about the large-scale elemental, chemical, and isotopic structure of the nebula. And so I'm going to actually start over here on the left with the Genesis mission. And I'm not going to have very many plots here, so I apologize for data plots. But this I can't resist showing because this is probably the most important plot in planetary science because it is so fundamentally mysterious. We do not understand it. So I should first just ignore the plot for just a minute. If you do not know what isotopes are, I'm going to do a very quick sort of sidebar on what isotopes are. So in nature, almost every element has many different flavors, and they are distinguished by the number of neutrons in the nucleus. So oxygen in particular has 3 flavors that are stable, 3 different isotopes. So oxygen-16 is the most common. Every oxygen in the nucleus has 8 protons, but oxygen-16 has 8 protons and 8 neutrons, 8 plus 8 being 16. But there are 2 other isotopes of oxygen. Oxygen-17, which has 1 extra neutron, that has 9 neutrons in the nucleus, and oxygen-18, which has 10 neutrons in the nucleus. So there are these 3 stable isotopes of oxygen. And it turns out that in the Earth, if you pick up any rock on the Earth, that the relative amounts of those 3 isotopes is very well understood. And it falls in a line on this plot. So this is the amount of oxygen-17 in something, any object you might want to pick up. And what we're doing is we're expressing it in a notation where we're talking about the deviation from seawater. So you take seawater as your standard, and then you ask, okay, here's a rock. We're going to measure the amount of oxygen isotopes and ask how much it differs from seawater. And that's this delta 17 oxygen, for oxygen-17, and this is in parts per thousand or parts per mil, so that's what that notation means. And this is oxygen-18 down here. So we're plotting each one of these points as an object. It's an object you've picked up and you've analyzed in the laboratory. So the Earth is up here, and you can find anything on the Earth that's going to fall right on this line like that. One of the big surprises from Apollo was that the Moon has identical oxygen isotopic composition to the Earth, which was a huge surprise. And it's actually kind of amazing, and it leads to this idea that the Earth and the Moon must have formed a collision of a Mars-sized object into the Earth that produced this sister planet, really, to the Earth. It's almost what it is. So, about 30 years ago, a guy named Bob Clayton in Chicago, University of Chicago, was analyzing meteorites. And he was not even bothering to measure oxygen-17. He was just measuring oxygen-18 because he figured, this is going to be boring. Then he said, well, okay, I'll measure 17 and 18. And he found this amazing thing, which was that a lot of meteorites or components of meteorites don't fall on this. They fall on this weird line. And this line is such a fundamental mystery in planetary science that it's been a major effort in the whole field to try to understand this ever since. We just don't, and we still don't understand it. But one of the main things we didn't know was where is the sun in this plot? So the Earth and the Moon are up here, and then you have meteorites that are also up here. Mars is that little red thing. It's different than the Earth, very, very slightly. So the Genesis mission flew ultra-clean, ultra-pure collectors at the L1 point. The the L1 point is the point between the Earth and the Sun where the gravitational attraction of each balances each other out. And so it isn't quite stable, but you can hang out there relatively easily for a long time. And so the Genesis mission did that. It exposed these collectors to the solar wind for a couple of years and then came back. And a guy named Kevin McKeegan at UCLA measured the position of the sun. So here is the solar wind value, and here's where the sun is, we think. It's just this slight difference has to do with sun affecting the solar wind. So this puts the sun right down here, which was, again, a big surprise. Nobody knew whether it was going to be here, or way up here, or anywhere else in this plot, but it's down here. So there are a couple of theories for why that's true. And I'm not going to talk about these in any detail. One is called photochemical self-shielding, and another one is mixing between two different kinds of reservoirs. Both of these ideas have major problems. My particular opinion is that both of them are probably wrong, but we don't have any good ideas for what is causing this weird pattern. So this is just one of the fun mysteries in planetary science. Meanwhile, at the other end of the solar system, we now have, so we have lots of material from here. We in fact have tons of meteorites, literally, tons of meteorites, but hardly anything from out here. So that was the purpose of the Stardust mission, was to collect the first samples of material from way out in the Kuiper Belt. This is this lovely image from the ALMA collaboration. This is an image of a protoplanetary system with very clearly these lanes cleared out from the disk where there are undoubtedly planets. You can't see the planets, but you can see the lanes that have been cleared out by them. And this is a plot which just shows the amount of material, collection mass. This is a logarithmic plot versus heliocentric distance. If it's a little hard to digest this very quickly, all I want to say is that the stuff from out at the edge of the solar system is underrepresented in our collections by about 13 orders of magnitude by comparison with meteorites. And so it's obviously important to get some of this material. And so, and we think that 99% or more of the small bodies in the solar system, in fact, are Kuiper Belt objects, not asteroids. So this was the point of the Stardust mission. So Stardust was a Discovery class mission. Discovery class means that it costs something in the order of $300 million. That sounds like a lot of money, but you can put it in some ways that don't make it sound not quite so expensive. So that's about the salary of a well-paid baseball player for about a decade. So maybe it's not so bad. And so I should say this is about the size of the VW Bug or so. And in January 2004, the Stardust mission flew through the coma of a Jupiter-family comet, the comet Wild 2, at about 6 kilometers a second. And then in January of 2006, it brought back those samples in a sample return capsule. We'll see this again in a few slides. This came back from the Dugway Proving Grounds in Utah, so west of Salt Lake City. The collecting material that was used by Stardust was a weird material called Aerogel. And I've got some up here I brought with me. It's not Aerogel from the Stardust mission. If I had brought that, I would go to jail. But it is Stardust. It is Aerogel that was made by the same guy who made the Aerogel for Stardust at JPL, a guy named Steve Jones. And so one of the things that we had to do when the Stardust mission came back was to figure out how to get the particles out of the aerogel collectors. And to do that, we borrowed tools from microbiologists. And the result was little things like this. So this is a little doorstop-shaped wedge of aerogel, and it contains a cometary track. So here's a particle that came in from the comet. This was the original surface. And as it came into the aerogel, it broke up into tiny little pieces. This is a very fragile particle. Turns out that almost all these cometary particles are very fragile, which is maybe not too surprising. And so each one of these little tracks here is the result of a slowing particle which stopped at the end of the track. And that's what all these things are. So for scale, this whole length of this thing is about 1 millimeter. So this is a really small object, and it'll get worse. So this is a gigantic track for us. This one is 13 millimeters long. And it's a very famous in our community, very famous track, track 41. A huge amount of science has been done on this. I don't know how many papers have been written about analyses that have been done on this track. I bet something like 20. And there are a number of mysteries about this. But yeah, I just show this because it's a lovely track. And here's one of the places where we extracted a keystone, one of these doorstop-shaped wedges of aerogel containing material from the top of that particle. Oh, but the point I wanted to make of this also.
Which way is it going?
Sorry, yeah, I should have said. Particle came this way, so it was moving left to right in this picture. So these particles are made of very tiny rocks. The tiny parts came apart and then stop in this upper bulb kind of region in the aerogel. And then the large objects, the really big hunking rocks that were incorporated into this original thing, make long tracks. And this particular one right here is very interesting. It's a particle called Sameo. They all get names because we just can't remember the numbers that NASA assigns them. And so you might ask, well, where does oxygen, where does this comet fall in this oxygen isotope plot that I showed earlier? And here's where they are. So they are also on this same line that Bob Clayton discovered at the University of Chicago 30 years ago. Okay. What does that mean? How could that be that that's at the edge of the solar system and we're still seeing the same pattern? It's really a puzzle. So we're collecting more data now. And one of the things that we did recently was to look at this really fine-grained stuff and see if it was any different. And we found that it was. So working with colleagues at the University of Hawaii, who have an ion microprobe, it's an instrument that can measure isotopic composition and measure the relative amounts of each of these oxygen isotopes in really tiny samples. What we found was that stuff was way up here on this plot. This is pointing towards maybe the idea that there were two distinct reservoirs that went into making up the solar system. So it's pointing in that direction, but that theory still has some major problems. And so, we're still all collecting, we're still scratching our collective heads, trying to understand what we're seeing here. So another question here is, how did material move and evolve in the nebula? This is another cartoon. This is showing the structure, what we think might be the structure of the solar system in the early days. And this is, again, a logarithmic plot. So here's 0.1 AU, here's 1 AU, where the Earth is now, 10 AU, 100 AU. We think that stuff originally had to come from the interstellar medium. So it came in this way, and then it was subjected to shocks, we think, in the outer solar system. And then some of these things collected into objects which eventually became melt droplets called chondrules, and I'll show you some lovely pictures of these in a minute. And then some of the stuff from the very close to the early sun, we think may have moved out from the early sun out to the outer part of the solar system. So why do we think that? Well, I showed you that picture earlier which showed the bipolar jets. So okay, so that may say, fine, well you can imagine that there's some of that material that may fall back onto the disk or something. Okay, maybe it'll be some sprinkling of stuff, but really how much of it is there? So, let's skip that slide. One of the challenges, though, is to analyze these particles while they're still in the aerogel so that you can do a comprehensive study. So, this is the same keystone I showed earlier, showing all these little particles in the aerogel. So we developed a technique using the advanced light source. Again, it's this building across the bay at Lawrence Berkeley Lab. Fundamentally, it's an X-ray microscope the size of a small shopping mall. And so this is what we use to analyze the Stardust samples. Among others, this is a synchrotron, and we use this and other synchrotrons around the world, in Europe, Japan, and 3 others in the United States. And one of the things that we do is we look at iron. So iron turns out to be very interesting. If you're a chemist, you know that iron is a transition metal. And so whether iron is in a metal form or a sulfide form, or if it's an oxidized form, so iron 2+ or iron 3+, that tells you about how much oxygen there is in the environment. That turns out to be very interesting. And we can use a focused X-ray beam to measure the oxidation state of iron. Is it metal, sulfide, or oxidized iron? While the particles are still in the aerogel, we don't actually even have to pull them out. We can look at each individual one of those particles. And so what we found was a huge surprise. So we were thinking, okay, there's going to be a sprinkling of material from the inner solar system. And I'm skipping over a lot of details because I don't have time to talk about it. But it turns out that more than half of the stuff that went into Comet Wild 2 at the edge of the solar system, in the Kuiper Belt, beyond 38U, cycled through the inner solar system at some point during the solar system's history. Who ordered that? Enormously surprising. And we're seeing lots of other evidence as well, that there must have been some kind of a grand conveyor belt, which not only brought material into the solar system, but threw it back out again, and then probably cycled it many times. Weird. So, I mentioned before these CPIDPs. These are the particles collected in the stratosphere by high-flying aircraft, some of which fly out of Ames, by the way. And this is one of those particles collected on a silicone oil-covered plate. And these are really fascinating objects. They're tiny, tiny agglomerates of even tinier rocks held together by a kind of organic glue. And CP stands for chondritic porous. It's just a description of its composition and its structure. And IP, again, is interplanetary dust. For a long time, people thought that these must come from comets. But when we compared, and I promise not to have too many plots, and I'm having a lot of plots, okay, I apologize. But this is a so-called ternary plot. If you're a geologist, you may be familiar with these. So iron metal up here, sulfide and oxide. Here's our measurement of the oxidation state of iron from Wild 2, and here it is from CPIDPs. These are very different. So this raises the question, in fact, do these things that we thought were cometary, maybe they don't come from comets after all, but if they don't come from comets, they almost certainly don't come from asteroids. Where do they come from? So it's a real mystery. That particle that was at the end of that long track I mentioned earlier was a big surprise. This is a particle that got its name Cineo, and it turned out to be a hunk of metal, a hunk of iron nickel metal with a weird composition. With very, very low nickel compared to other kinds of metals that we find. So what's a big, gigantic hunk of metal doing on a comet? So we just, what we're finding is we're just raising more questions than answers, which of course is what makes it enormously fun, right? And then what is really becoming interesting then is maybe the answer is not that these IDPs don't come from comets. Maybe they just come from different parts of comets than what we sampled with the Stardust mission. And a hint of this comes from Rosetta. So the European Rosetta mission has spent 2 years, 2 years or so, in the vicinity of Comet 67P, and made all kinds of amazing observations of this comet. This is also a Jupiter-family comet, like Wild 2, probably formed in the Kuiper Belt. And among the many weird observations from Rosetta is this observation that that this comet looks like almost like a sedimentary rock. It looks like it was built in layers. And so maybe what happens here is that these comets are actually very heterogeneous. Maybe we have a core that's formed early in very, very primitive materials, and then stuff that, because of this gigantic conveyor belt that brought stuff in from the inner solar system, layered on top of these comets so that the outer parts of the comet have a very different composition than the inner parts. Okay. How, when, and where did the macroscopic components of the solar system form, and in what order? So here is asteroid Itokawa that the Japanese Hayabusa mission visited. Here's a picture of Wild 2, Mars, of course, and Jupiter. When I say macroscopic components, though, I don't just mean large objects, but I mean things that are bigger than the building blocks. And so these are these CAIs, these calcium aluminum-rich inclusions. These are, we think, the first objects to condense out of the hot solar nebula. And these are the things that populate that weird line on the oxygen isotope plot. These are petrographic, by the way, petrographic sections, so they're just lovely to look at in a microscope. If you ever have a chance, it's like looking at a stained glass window. They're just beautiful. This is a chondrule. These are these melt droplets that I mentioned earlier. And this is one of the, again, fundamental mysteries in this field. These are melt droplets, very clearly, but we don't know how they formed, even though we've recognized them for 130 years or so. So one of the tools we have, and we want to understand when these things formed, is an isotope, another isotope. This time it's an isotope of aluminum. Aluminum has one stable isotope, aluminum-27. So aluminum can, all the aluminum in aluminum can is one isotope, aluminum-27. But there's an unstable isotope called aluminum-26. It's radioactive, and it can be used as a clock, so we can measure age. We can measure the age of objects using this. And so it turned out that the amount of aluminum-26 in the early solar system, about 45 parts per million of aluminum was aluminum-26. It's all gone now, because it's only got a half-life of 700,000 years. So it decayed away long ago, but we can detect its daughter. What it decays into is magnesium-26. So by measuring the amount of excess magnesium-26 in the rock, we can tell how much aluminum-26 it had when it formed, and that in turn tells us when it formed, with respect to the beginning of the solar system. So I want to talk about a particular particle called Iris. And Iris is that little particle right there at the end of this another famous track, track 74. First we did a bunch of analyses on the synchrotron of this thing. We mapped in metal, in iron. We also did chemical maps. So this is an iron, chromium, nickel X-ray map of Iris before it was extracted. And Iris was actually named not by me, but by this munchkin who is now 15 in high school. But she was, I think, 7 or something like that at the time. She knew Spanish. She looked at the X-ray picture, and she knew that Iris means rainbow, and so she said Iris or Iris. That's how it's got its name. And now that name is in several papers, including papers in the Astrophysical Journal, kinds of things. So, and this is, by the way, the sample return capsule for Stardust on display at the National Air and Space Museum in Washington, D.C. And we were there sampling that capsule as part of our Interstellar dust project. So here is Iris. It also turns out to be a tiny little melt droplet. Who ordered that? Except that the poor thing is only about 13 microns in its biggest dimension. So it really does look like a melt droplet, and it's a rock in the classic sense of a geological rock. A rock is a collection of different minerals, and Iris is a collection of different minerals. Chromite, olivine, spinel, and other things in a glassy matrix, and so it's a rock, but it's only 13 microns in diameter. So what we did was we first looked at it on the synchrotron, and then we embedded it in epoxy, and then we used a diamond knife to slice parts of Iris up in 100 nanometer thick slices, and put them onto particular special kinds of grids. And we did all kinds of analyses on this, using electron microscopes, X-ray microscopes, and I won't go into any detail in any of this, but one of the things that we found were phases that allowed us to do this aluminum-26 dating. And we used a really cool thing called a FIB at the National Center for Electron Microscopy. It was a saga, it took years. But one of the things we found was that we were able to use the aluminum-26 abundance in this thing, and we could tell that Iris formed at least 3 million years after the beginning of the solar system. Why is that interesting? So it turns out that we think Iris formed in the inner solar system because of some other lines of evidence. Once Jupiter formed, it carved out a big gap in the disk, which would not have completely suppressed, but it would have mostly suppressed any further material from transporting from the inner solar system to the outer solar system. So what that means is, if Iris formed at least 3 million years after the beginning of the solar system, now we find it way out at the edge. That's where it got into the comet. But it formed early in. That tells us when Jupiter formed. So this tiny little thing, it's only 13 microns in its biggest dimension, is telling us about the timing of the largest object in the solar system other than the sun. And this is the list of analyses we did on this poor little thing. And what's really cool is that we only used up about 10% of it. So 90% of the particle is still available for future generations of scientists to study with instruments that maybe we can't even imagine today. So this is one of the big advantages of sample return. We feel feel so fortunate in our lab to have these samples to work on. We can analyze these samples for decades. We can do repeatable measurements, not just one measurement, but we can do several. We can send them to our colleagues. They can do tests. We can do repeat measurements and make sure that everything's right. We can use instruments like the Advanced Light Source that could never, ever be flown in space. Well, I shouldn't say never, but it would be really hard. We can use instruments that did not exist when the mission was first launched. Several of the instruments that are now being used on Stardust samples did not exist when the mission launched. In fact, in 2 cases, even when the mission came back. And it sets the stage for new questions to be addressed by new missions. Okay, so let's come back to the top of this list. What fraction, if any, of the primitive construction materials survive, and how can we recognize them? Here's another one of these chondritic porous interplanetary dust particles. And one of the things that people have suspected is that some of these objects in here are in fact interstellar. They're not things that form in the solar system, but they form in the interstellar medium and then got incorporated into these tiny little things. And one of those kinds of particles is a really enigmatic kind of particle. It's called a GEMS. That's an acronym. It stands for glass with embedded metals and sulfides. This is one of them. Notice the 200 nanometer scale bar. That's 200 millionths of a meter. This is a really tiny object. But these are very commonly found in these chondritic porous IDPs. And these might be some of the fundamental building blocks of the solar system. So we've been doing some fun things with these particles. We cut them in little slices across them. So here's one of these particles on a filter. And now my colleague Christy Julie Rehak has used the tool that I mentioned earlier called the FIB to slice this into a really tiny slice, and now we can see into the interior of this thing. And we can then analyze this by infrared spectroscopy using a new tool, totally new tool, that is called nano-FTIR. It's a way to do infrared spectroscopy on samples with resolution about 100 times better than anybody could do up until then. And this is our view of that particle. This little thing down here is a GEMS, and then we were able to make an infrared spectrum of this GEMS. And it is not at all what we expected, because we expected this to look like something that was irradiated, but it's got a totally different spectrum. So again, we're going back to the drawing board and saying, okay, everybody's ideas about GEMS are probably wrong. Okay, so back to this cartoon, and let's go all the way out beyond the edge of the solar system, beyond the Kuiper Belt. So, as Linda said, Stardust is 2 missions in 1 spacecraft. It had a collector which faced forward, and it collected about 300 micrograms of material from this comet-filled tube. But it also had a backwards-facing collector here. And by the way, this is about the size of a stop sign, this collector. And this was exposed to the stream of interstellar dust that comes into the solar system because of our relative motion with respect to the local interstellar medium. And it was exposed for about 200 days. And we expected to get something like 100 particles as a result of this exposure. So we started a project, I guess it was really about 7 years ago, called the Stardust ISPE. ISPE stands for Interstellar Preliminary Examination. So a preliminary examination sounds kind of boring, but it's a NASA term. The very first PE was the Apollo PE, preliminary examination, to look at the Apollo moon rocks and just say, all right, what do we got? And how do we inform people of how do we characterize these things so that scientists can request samples in some intelligent way? So for the ISPE, this turned out to be a multi-year project, much longer than we expected because it turned out to be so hard. So this was 6 related projects. One was to identify impacts in the aerogel collectors, and I'll come back to aerogel in a second. Then we had to develop techniques for extracting particles, these tiny little things, from the collectors in what we call picokeystones. Then we did synchrotron analyses at the ALS and at other synchrotrons. We also actually took advantage of the fact that the collector had aluminum foils in it, which were not even intended to be collectors, but turned out to be really useful by accident. to look for impacts in those foils. Then we had two supporting projects. One was to do shots at the University of Heidelberg in Germany, very high-speed particles into aerogel to just understand what do the tracks look like when you shoot a particle into aerogel at 20 kilometers a second. And then some numerical simulations of dust coming into the solar system to see how things move in the solar system. That helped us to understand what we saw. And this was a vast project with 63 professional scientists, but more than 30,000 volunteers. And this was a project called Stardust at Home. And we did this completely out of desperation. So the problem is, we have this collector. It's about the size of a stop sign, about 1/10 of a square meter. And we needed to find the impacts. We knew that there would be a few dozen particles in the collector somewhere, but we didn't know where they were. And in order to find them, you need a really high magnification. And so when you did the math, it turned out that it would be searching like something like 1 billion fields of view. No way we could do that with our tiny little research group. And then we thought about, well, we'll write some kind of computer-based thing to find these tracks. And we realized we didn't know how to do that. And so I went down the hall to my colleague Dan Wertheimer, who runs the SETI at Home project, and said, can I steal your name? Or steal at least the name, the idea for your name. And we started the Stardust at Home project, which is using a web-based virtual microscope. It uses images collected by an automated microscope, images that are aerogel collectors, and then you have a slider which moves up and down. It focuses through these images, just as if you're looking through a real microscope, except you don't get a crick in your neck. And we can have thousands of people searching simultaneously. So this turned out to be very successful. So it's actually more than 33,000 people who volunteered to do this, and it is actually non-trivial even to get started, because you actually have to do some training and testing before you can even start. And that this group of people has done more than 100 million searches of images and have discovered more than 200 tracks in the aerogel. And so this has turned out to be quite successful. Nobody could have predicted, I certainly couldn't have predicted how successful it would be. And it's led to a very interesting spin-off that I'll come back to in a second. Okay, so then we did analyses. We did extractions of the particles in these little tiny wedges of aerogel that we extracted using microbiology tools. I said before that these are the most challenging extraterrestrial samples ever collected. Actually, it's not really true. The Interstellar collector is way more challenging because the particles are 1,000 times smaller in mass than the cometary particles, and there are maybe 1% at most, as many of them. So there aren't very many, they're really tiny, it's pushing all of our techniques to their limits. But we found 7 particles that we think have an origin outside the solar system. So the first one we found is a particle called Orion, and it was discovered not by us, but by a guy named Bruce Hudson, who lives in Ontario, Canada. He's a retired carpenter, and as part of our deal with the volunteers, we said, if you discover a particle, if you're the first discoverer, you get to name the particle, and you get to be a co-author on any papers we write. So he was a co-author on our paper in Science, announcing the discovery of our 7 particles. So it turned out this particle has a mass of 3 picograms. A picogram is 10 to the minus 12 grams. It's a density less than water, 0.7 grams per cubic centimeter. It has olivine and spinel, 2 pretty common minerals, but also an amorphous magnesium-bearing, I wouldn't call it glass, because we don't know if it's really a melt, but it could be, but at least it's amorphous, and then an iron-bearing phase, which is different than all of those. And this particle is still in the aerogel. We have not extracted it yet. Second particle is called Heidelberg. This is a magnesium map, X-ray map. This is a silicon X-ray map. We were able to get X-ray diffraction in the synchrotron in Grenoble in France. And we were able to do spectroscopy and all kinds of other things on this particle. This is a little bit bigger, 4.4 picograms. It also has crystalline olivine and again an amorphous phase, but it's a totally different spectrum in magnesium. And so we don't understand why they're different yet. We're still trying to understand that. Then there's another particle called track 40. If you speak Russian, then you'll know what that means. And there's the track. The track itself is gigantic. You can can see it in the optical image. Here's what it looks like on the synchrotron. This is the carbon map of this particle. It's got a little bit of iron in it, but we think that particle came in at huge speed and mostly vaporized in the aerogel. Even in the aerogel, it vaporized. Then we found 4 particles that were in the foils. There's one of them right there. Looks like that. And among the 25 craters that we looked at, 4 of them look like they have interstellar origin. Okay, and so I'm a planetary scientist now, but I used to be a physicist, so it's very gratifying to have this appear on the cover of Physics Today. But more to the point, this is what the collector looks like. So these are the aerogel tiles, 132 aerogel tiles, and you can see the foils between them, which were actually originally only there just to be able to get the tiles out. Okay, so now let me talk a little bit about some frontiers, and some of those frontiers are on missions, and some of them are on instruments. And some of them are on samples, and this is one. This is a particle we recently discovered called Andromeda. This is a section of Andromeda cut with a diamond knife. All this stuff is iron sulfide, so it's not actually all that interesting, although it's got some interesting features. But the main point of it is that it served sort of like a heat shield. When the particle came into the aerogel, it protected material that is super fragile that happened to be right next to it. And it wasn't spinning, and so it just came into the aerogel and stopped, and it protected all of this stuff really, really rare in the Stardust material collection. So we're taking a lot of time to very carefully study all this. FGM stands for fine-grained material. Very clever, I know. And so we're still trying to understand this, but we're very excited about it because we think this may be the most primitive material anybody's ever seen, because of the fact that it happened to be protected by this big sulfide. So I want to talk a little bit, just mention a couple of other instruments that are really cool and new. So one of them is a technique called atom probe tomography. And this is being used not on Stardust samples yet, but it has been used on meteoritic nanodiamonds. This is an instrument that allows you to take a particle, an object apart, atom by atom, and you can tell not only where the atom came from in that sample, but what its isotope was. So you can tell carbon-13 from carbon-12 and so on. And each one of these tiny little dots is an individual silicon atom in this nanodiamond. So this is counting individual atoms in the sample. It's amazing. And it's super clever how they do it. A new instrument also is being developed by my colleagues and another group at Chicago. Chile, the Chicago Institute for Laser Ionization, is an ion microprobe that will be able to do isotopic analysis on almost the entire periodic table with almost complete efficiency, close to 100% efficiency, 40 to 50%. That doesn't sound close to 100, but by comparison with other instruments in the past, where it's like 1.1%, this is amazing, and so it's also very exciting. Okay, I'm going to skip over that to this one. This is from my colleague Rhonda Stroud at the Naval Research Lab. Here she can do X-ray analysis, X-ray fluorescence analysis on single atoms in a particular sample. Here she's looking at a silicon, one silicon atom, and this is an X-ray spectrum where you can see this peak from silicon in this, and it's just due to that one atom. Again, really just phenomenal advances. Okay, I mentioned the Stardust to Home spinoff. This is something that we just launched about 2 weeks ago, and I'm really excited about it. So I guess it was about 6 months ago we were approached by a group at Cornell that does Alzheimer's research, of all things. They had a problem, which is that they use mice that have an Alzheimer's gene inserted into their genome. Turns out wild-type mice don't get Alzheimer's. I didn't know that. But a tiny fraction of human Alzheimer's comes from a particular, is genetic, and we know what the gene is. So they took the gene, put it into mice, and then these mice get Alzheimer's 100% of the time, which is great for doing research because it means you can do experiments, and you know that they're going to get Alzheimer's, so there's no question about it, and then you can try different treatments. So what they want to do is, four little things. What they do is they cut off the top of their cranium, skull, and they replace it with a cover slip with superglue. If you didn't know, superglue was originally developed for surgery. So they superglue this cover slip on, and then they do imaging of blood flow in the mouse brain while the mouse is still alive. And the goal is to understand and count and map stalled capillaries in the mouse brains. And they'll try experiments and treatments and then see what happens to the blood flow. Because it turns out Alzheimer's is basically a vascular disease. And so this is what one of those images looks like. It's very noisy, it's very ratty. I find it's very hard, but some people are really good at it. And the point is that it takes them a few hours to collect the data, but it takes them like 6 months to a year to analyze the data. But it's something people can learn to do, just like looking for interstellar dust. And so the virtual microscope that we developed for Stardust at Home has now been adapted for this project. And we hope that it's going to accelerate their research in Alzheimer's disease dramatically, by at least a factor of 10, maybe more, so that maybe no longer this will be their bottleneck. They can do experiments much more rapidly. So when we started the Stardust at Home project, we didn't have anything like this in mind. And then finally, I want to mention a new mission. So this is the OSIRIS-REx mission. It launched about a month ago, I think. And its goal is to collect 60 grams of regolith, that is soil, from a particular kind of carbonaceous asteroid. It's going to be coming back in 2023. And then NASA has announced a new opportunity to apply for a so-called New Frontiers mission. These are billion-dollar class missions. And one of the ones that has been announced as a goal, as a target, is to go to a comet, perhaps like 67P, the one that Rosetta went to, land on the comet, collect at least 500 grams of material, and bring it back to Earth. That would be enormously interesting, because although we've gotten a lot of fabulous science out of the Stardust Vil-2 collection, those particles were collected at 6 kilometers a second, and so the organics particularly got creamed. The rocks survived great, but the organics got creamed, so we'll be able to do all kinds of things with organics analysis if we can get the sample. Okay, so I'm going to show a bunch of pictures very quickly, and probably most of you have seen a lot of these pictures, but they're just irresistible anyway. So these are images of the Pluto-Charon system from New Horizons, and finding all kinds of weird things. So this is a solid nitrogen lake, apparently convecting. It has these just strange features. These are pits that are like 5 kilometers across and a kilometer deep. Huh? What's that? They're all over the place, and there are these weird patterns that look, just strange. Here's again 67P. This is Churyumov Gerasimenko. Look, and it, other than looking like a rubber duck, it has again this sort of weird structure that looks like sedimentary rock almost. And also, there are regions that look like goose flesh. So these structures that are maybe a couple of meters across, boulders or something. We don't know what those are, but they seem to be in a lot of different places on this comet. And then, of all things, these look like things you see in the desert. They look like aeolian features, wind-driven features. But this is an airless body. So nobody knows what these are. And as far as I know, there aren't even any really good ideas. And then, I guess it was 2 weeks ago or so that the spacecraft actually crashed onto the surface of the comet and ended its mission. And so that wasn't this morning. This is from a different talk I gave about 2 weeks ago. Okay, so other new missions that have reported data. Another mission called Dawn made a geological map of Vesta, a dwarf planet in the inner solar system. And so I think here's what I want to say, almost to close. So we think we've now visited with spacecraft every type of body in the solar system with spacecraft and done in situ measurements and imaging. But I think that it's fair to say that sample return, getting the samples from those bodies and bringing them back to the lab so we can analyze them in the kind of detail we can with these instruments, has got to be what's next in solar system exploration, or at least a big part of that. And it's already reflected in NASA priorities. And so to put this in some context, in terms of how much we've improved. So this is a view of comets in 1577. This is our view of comets in 2015. And those are individual atoms in a particle called Cecil. And a similar kind of, so that's 21 orders of magnitude improvement in spatial resolution. And then we think this is our view of interstellar dust in the galaxy. And now this is, we think, our view of interstellar dust, and it's about a 27 order of magnitude improvement in resolution. And so we think that this is going to be the future, is to do even more like this. So I'll leave you with this thought. Thank you. Before I take any questions, and I invite questions, I want to say I brought some Aerogel. I forgot to mention that earlier. And after questions, if you would like to see Aerogel up close, please come up. Yes?
So I have a question about the formation of material. You talked about whether it's been formed in our own solar system or whether it's formed before. The sense doesn't give it engineering
Right.
and so all of that depends on computers from two numbers of the Earth and study on creation. And I guess I'm trying to connect to the root for our own solar system. And you're trying to say that there's other things that are formed or
Right. So when I'm talking about things forming, absolutely right. The atoms in the solar system were formed in almost entirely. Were formed in generations of stars long before the solar system formed. Some of those, when I'm talking about things forming, what I mean is solid rocks. So are there solid rocks left in the solar system that predate the solar system? We know that there are. They're so-called pre-solar grains. They exist in meteorites at about the part per million level. And we can recognize them because of the bizarre isotopic ratios that they have in carbon and silicon. Way bigger than that oxygen isotope plot I showed. If you try to plot these pre-solar grains on that plot, they're way off the plot in all different directions. So they're really wild. But then there are lots of other things that are in the solar system that may be that they formed before the solar system formed. But we don't know how to recognize them yet because they don't look any different than anything else. So I think it's largely an open question. But in terms of the atoms, yes. Vast majority of the heavy elements in the solar system formed along with the solar system. I'm not sure if that's a question.
So on that, Mercury, Venus, and the gas giants were all missing. Do we have any samples natural from these? Are you planning to go get them? If not, why not?
So that's a great question. So there are different answers for different parts. So to get one of the things that would be great is to get a sample of these. The problem is the logistics of actually doing it because of the fact that there's certain temperature Venus at the end of the sea and the thick atmosphere itself. There have been missions proposed to do that, but nothing has been approved yet. Mercury is much more practical, but and in fact, there was news there was an idea that somebody maybe had a meteorite from Mercury, but the problem is that it's very energetically difficult to get the mission there to come back. There is a proposal, an idea out there to go to Enceladus. So Enceladus is wonderful because it has these geysers, and so you don't have to land on Enceladus to get a sample. You can fly through a plume and in principle get that. But it's still the reason we can get these samples of Kuiper belt objects so inexpensively is because of the fact that these comets happen to have been thrown into the inner solar system when they get to them. To get out to the Jupiter system or Saturn system and do a sample return is a multi-billion-dollar and very risky.
So you don't have to look in.
Exactly. Right. But those would be fascinating samples to have, absolutely. Yes?
On that oxygen isotope composition chart,
Yeah.
it's the slope of that line.
One.
Okay.
It's actually 0.9.
And that's not understood as well.
See if they mark it there.
It is not understood. It may be a so-called mixing line, so a mixing between two different reservoirs, maybe. But